This is going to be a super quick video just going back over what resonance means. And sometimes we have some equivalent possible Lewis structures. And so we used resonance to represent equivalent Lewis structures. And usually what happens is that we'll have a double bond that there's more than one possible place for it, more than one possible place that's exactly an equal place to put it. And we will show, using resonance, we'll show the double bond in all of the possible spots. So for example, if we want to draw NO3, we have 5 plus 6 times 3 is 18. Sorry, this was NO3 minus, so that's plus another 1, and that is going to be 24 electrons. N is my central atom. I start with single bonds between the N's and the O's. That's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 gets me here, but my nitrogen is not experiencing an octet there. Whenever I don't have enough to go around, I take away a lone pair and I make a double bond. But the problem is that double bond has 3 different places it could possibly be. How do I determine which of those 3 places the double bond exists? And the answer is that we don't determine which place it exists. And in fact, it doesn't exist in just one place. Remember that those double bonded electrons are part of a pi bond. That pi bond exists out of plane. And in this case, it is going to be, because of the fact that this is trigonal planar, that second pair of electrons in that bond is above and below the molecule. And those electrons are actually moving from place to place. So what winds up happening is that if we measure, and there's a third one that I'm going to put down here. If we measure the bond lengths are actually identical. The bond length is not the typical length for a N to O single bond, nor is it the bond length for a typical N to O double bond. We actually wind up with an average bond length of 2 singles and a double, or approximately so, and all 3 bond lengths are identical, which tells us that these little pictures here, these resonance pictures, are snapshots in time because we have to have a way to represent it. So this is our way of showing that the extra pair of electrons is moving throughout the molecule. Another example of something that would have this resonance would be ozone. Ozone is O3. That's 18 electrons. And if we want to start trying to make it with single bonds, that's 2, 4, 6, 8, 10, 12, 14, 16, only gives me this single pair here on my central oxygen. So let me just do that again. 2, 4, 6, I don't think I counted right. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, I did. So now this central oxygen is not satisfied with its octet. One of these pairs is put into a double bond. But again, how do I decide whether the double bond goes here or here? And again, the answer is we don't decide. This structure is best described using resonance to show that the double bond is actually in both places over time. The electrons are moving between those two sides. The bond lengths are identical between the two oxygen to oxygen bonds, and their bond energy as well as their length is about an average of a single and a double bond. So again, they will give you the prompt to draw all possible resonance structures or something like that. And it will usually or typically be the placement of a double or a triple bond that we are moving back and forth.